Welcome. In this demonstration, we're going to look at the confusion matrix. And to begin with, we have to talk about data mining. So data mining is we're simply mining for patterns and relationships in data. And one type of data mining algorithm is a classification. So in a classification, we want to determine class membership. So examples of that would be which emails are spam and which are not. Which patients will die from COVID-19 and which will not. Which customers will purchase a given product and which customers won't. So these are classification problems, and a classification problem is binary. So either an email is spam or it isn't spam, right? There's no gray area here. It's either a 0 or a 1. That's a classification problem. Classification is supervised data mining. And in supervised data mining, we have to have a data set where we already know the answer to this question about class membership. And so let's think about an example with spam. We would start with content from emails that have already been labeled as spam or not spam. In fact, I have an example right here. This is a data set from Kaggle, which has lots of data sets to choose from. And there's two attributes that we're interested in for our discussion. And one of them is simply variable 1 and the other is variable 2. Variable 2 has the content of the email and variable 1 has the labeling. Now notice they were cute here and labeled it ham for a valid email and spam for, well, a spam email. Now to solve this classification problem, what we would do is we would divide this data set up into training and validation. So we would take a certain percentage of these records. There's over 5,000 records here. And we might take, say, 60% of these records and use them to train some software. Now, the software itself is written by someone else who knows a lot more than we do. And we're just using that software to solve our classification problem with the data that we have. So we divide it up in this training and validation, and we run the training set through this software to train the software on our data set. The classification software can use one of several algorithms, and here's some examples. You can have decision tree classification. You can have naive Bayes classification. You can have the K nearest neighbor classification or a support vector machine classification. Now these are examples, and again these are written by people who know more than we do, and we simply use these much like we use a function in Excel or in R and get the answer that we want. The training phase is where we use our data to train one of these algorithms, and we're doing that with already knowing the answer of which of these, in this case, which of these emails are spam and which are not spam, or ham in this case. Now, once we've trained the data set, then we've reserved about 40% of those records for what's called validation. And then we'll run it against the validation without letting the software know which ones are spam and which ones are not spam. And the results of that validation produce the confusion matrix. And so now we're going to dig into the confusion matrix. So a confusion matrix always begins with the understanding that we know, and I'm going to stick with a spam example, we know which ones are spam and which ones are not spam. And this is called our actual class. So we have those positives, so they are spam, and we have those negatives, they are not spam from our actual class. Now we're running this algorithm that's been trained, and we're producing the predicted class. Now with the predicted class, we also have the positives, meaning that our algorithm has identified certain emails as spam, and it's identified other emails as not spam. So that's the predicted class. And then we actually produce the confusion matrix with counts that go into these boxes here, where we intersect either the positive from the actual class or the negative from the actual class with the positive from the predicted class and the negative from the predicted class. So let's see what that looks like. So, well, first of all, here's an example of what a confusion matrix might actually look like. This example is from R. And notice that it has the reference and the prediction. So the reference is the actual class. And notice that it has bad and good. So in this case, it would be the negative results and the positive results. And then the prediction are the negative results and the positive results. So it's inverted from what I'm showing in my confusion matrix. So that's just an example that we have numbers in here. That's what's going to be produced by a confusion matrix. So we want to know how to interpret the confusion matrix. That's the purpose of what I'm going into here. So what we're going to look at is we're going to look at our predicted class, and the predicted class is going to produce certain positives. Now, some of those positives are going to be correct. They will be true positives, called TP, true positives. And some of those will be false positives, or FP. Now, the true positives are true because we already know in the actual class that these are positives. Remember, this is dependent on having a set of data where you already know the classification so that you can train the software and validate the software. Now, in addition to the predicted class positives, we're going to have the predicted class negatives. So we'll have a negative that is a false negative because it is actually a positive, even though our prediction class called it a negative. And we have the negatives that are a true negative because they are actually negative, right? So again, we have true negatives, TNs, and false negatives, the FNs. And notice that that's what's being shown here as well. Now, once we get those numbers, so that explains what all these numbers mean. Now, once we get those numbers, then we start doing some calculations to determine, well, how well does this algorithm work for us in classifying our data? And just as a reminder, remember that this is from the validation process. So our predicted classes don't, the algorithm at this point doesn't know which are positive and which are negative. So this is a true test of the validation of the algorithm that we've trained with our data. Okay, so we can start doing some calculations. The first calculation we're going to look at is called sensitivity. Sometimes it's called recall. Sorry, it's so confusing that we would use two different names for this, but you'll see this labeled either way, sensitivity or recall. And sensitivity is the true positives. Okay, so that would be this category right here, the TP, divided by the sum of the TP plus the false negatives. Notice that with the sensitivity, we're concerned about this column here. Sensitivity will provide us the percentage of the actual class positives that were correctly predicted by our algorithm during the validation process. Then we can calculate what's called specificity. Now, specificity is concerned with the actual class negative column, and the calculation for that is our true negatives divided by the sum of our true negatives plus our false positive. Again, you can see how that is in this column here. Specificity will provide us the percentage of the actual class negatives that were correctly predicted by our algorithm in the validation process. Now we can do some calculations on the rows, the predicted class and the positives for that. We have something called precision. Also, it's called the positive prediction value. And that is the true positive divided by the sum of the true positive plus the false positive. Again, notice how this is in this row here. And that's going to give us the percentage of the predicted class positives that are correct based on the actual class. And then we have, for the negative, we have the negative prediction value. And the negative prediction value takes our true negative and divides that by the sum of our true negative plus our false negative. And again, notice how this is in this row here. And that's a percentage of our predicted class negatives that are correct based on our actual class. Now we can do some calculations that involve all of the cells of the confusion matrix, all of those values. And the first one is called accuracy. Now, accuracy takes the sum of the true positive and the true negative and divides that by the sum of all of the values, true positive, false negative, and true negative, and that gives us our accuracy, and that's the percentage of the actual class correctly identified by the predicted class. And then we have what's called the error rate, and the error rate is taking into account our false positive plus our false negative, the sum of that, divided by, again, all of these, true positive, false negative, true negative, and that's going to tell us the percentage of the actual class incorrectly identified by the predicted class. So these are, if you will, global measures of our confusion matrix, accuracy and error rate. That's a lot to take in, and hopefully seeing it built one part at a time has helped you to understand the confusion matrix. Now there's more that we can do to practice with our understanding and kind of see how this works. And what I've done is I've copied this confusion matrix down and created an interactive example. So it's set up the same way. And here I have whatever the true positive is, whatever the false negative is, false positive and true negative, and then for each of these I have the values. So down here is what we modify. So notice that if I change this to 80, that all of these numbers are changed. Now notice that these are not linked, so this is not based on any specific size of data set. You would have to determine that yourself. Here's the confusion matrix example that I showed earlier, and let's plug these numbers in. Now this particular confusion matrix from R has these columns and rows reversed, so I'll have to pay attention to what I'm doing here. So positive is 127, and positive negative is 26, and negative is 80. Oh, that was already 80. Good. And then negative positive is 67. Okay, from this confusion matrix, we can see that the sensitivity is 65%. And what that means is that that algorithm that we had trained and then ran against the validated data correctly identified positives 65% of the time. And it correctly identified negatives 75% of the time, so that's specificity. And we have an overall accuracy of 69% with an error rate of 31%. Notice that these two are, they sum up to 1, okay? And that will always be the case. Also, we have a precision of 83%. So the precision, the positive prediction value of the PC positives, 83% of those are correct. And then we have a negative prediction value of 54%. So of the PC, the prediction class negatives, 54% of those are correct. Okay, so there you have it, the confusion matrix. Now you can build this. It will be excellent practice for you to figure out how a confusion matrix works, as well as give you a tool for interpreting the confusion matrix.